Now, to do the things that we need to do to describe various phenomena, we have to define a variation of the function, not just its snapshot, but the rate of change as you move along your coordinates. Let's call it derivative. And in this case, it's called lattice derivative. And you actually know it because that's how you learned calculus when you started. So I'm just reminding you something about your elementary calculus at the moment, but you haven't learned it in this particular way. So think of a hypercube in d dimensions with unit sides on it. And each edge is described by what we'll refer to as a unit vector in direction mu. So it's a set of unit vectors. The hat is for unit, and these guys are really d-dimensional vectors, all of them, because they're embedded in our original continuum in d dimensions. And this is a unit lattice cell. And what this particular edge of the cell does, it points muth direction. So now we're in position to define a forward lattice derivative. And because we're in higher dimensions, all derivatives are directional. So derivative in direction mu, which is 1, 2, 3 in 3 dimensions, of our continuum field, but evaluated at lattice port L, can be defined as the field at a lattice point compared to the field one lattice spacing away in a mu direction, let's say first direction. And the difference of these two things tell us how the field is changing as I move the smallest possible step. And to scale it correctly, I have to define it by the distance, which is lattice scaling. Or in our index notation, it's L plus n mu derived compared to the field at point L divided by A, and that's obviously a derivative. Now, there's lots of freedom how you define the discrete derivative if you're only interested in continuum limit. There's some problems which already live on a lattice, like various crystals in physics. So in those cases, you cannot take the limit. But if you can take the limit, you can also define, for example, a backward lattice derivative. So it's in the same direction, but you're comparing a point, for example, which was not one step forward in a positive direction of a unit cube hypervector. But one step back. So there's a minus here. Compare it. And you know, this is also a derivative in index or vector notation. That's what it is. And the reason why we care about this minus signs, in some sense, you know, this derivative is working backwards. And it's really, you'll see, we'll write this as matrices operation. With matrices, it's actually transpose of this. Of the one defined above.